Hi there, and thanks for joining us for this webinar on how to really unpack the next generation science standards. My name's Francis Vigent. Just to give you a little bit of background on myself, prior to NOADM, my experience is as a high school math teacher and an elementary and middle school science, technology, engineering, and math specialist. And I spent about 10 years in those various roles. And what we're going to talk about today is not unpacking the next generation science standards during this next hour sort of one by one and going through each of them simply because we don't have enough time in an hour to do that. What we're going to do, and what I hope to do, is to take some of my experience here from NOADM, but also from the class, to help you understand how to unpack the next generation science standards with your teams. So whether you are, or even for yourself, whether you're a classroom educator, kindergarten through 12th grade, or a lead teacher, a department chair, a principal, a curriculum lead for a district, or so on. So in thinking about how that's structured and how our time together is structured here today, what I'd like to do is start by really talking about the intentions behind the standards and how, as teams or individuals, we can go about discovering the intentions of these new standards. Specifically, looking at science and engineering and really how these standards look at that differently and the role of higher order thinking. And then going further with our teams to understand the structure and design of these standards, which are in fact performance expectations. And when we hear things like three-dimensional learning, what does that really mean? And as we think about the sort of unpacking process, what are the observable features of mastery level learning and the kind of shifts in teaching and learning pedagogy that need to occur in our classrooms? And finally, what I'd like to do is wrap up with some discussion of how do we develop and find well-aligned NGSS resources. And so in each of these stages, what I'd like to do is also direct you to resources and tools which are really great to use either on your own or with teams of folks as you engage in this process. So with that said, I do have to apologize. If you were on the live session, we had an issue with the recording. So this video recording is going to be a slight difference because none of this is scripted, but we are going to go through sort of the same talking points and same discussion as best we can. At the end, if you have any questions, if there was something that you were a part of on the live session that you'd like to get further explanation on, we'll give my contact information at the end of this presentation. And for those of you obviously viewing this for the first time, if you do have any questions, feel free to reach back to myself, to Mary Ellen, or to anybody else here at NOADM. Again, you can do that with the information that I'll provide at the end of this webinar, or what you can do is just go on noadm.com and click at the top of the screen. You'll see resources, about. Click about and then contact us. So with that said, let's jump right in here. So discovering the intentions behind the standards. The best resource that I can direct you to for this is this link that you'll see at the top, nextgenscience.org/get-to-know, K-N-O-W. And with the sections that you're going to want to read at this link, so you're going to come to a page that looks like this. The sections that you're going to want to take a look at are the sections labeled Front Matter, Appendix A, which is Conceptual Shifts, and Appendix H, which is the nature of science and engineering. And the reason that you want to take a look at these three documents in particular is that the front matter really helps to frame where these next generation science standards came from, really help articulate it in terms of why there is a need for new standards. Appendix A deals with the conceptual shifts between the old sort of fact-based standards that used to exist in most states in cases where there is an adoption. And even in states where there's an adaptation, the states that have adapted next generation science standards are states which, by adapting, those states that adapted did keep things like science and engineering practices and really a lot of the components of the next generation science standards. But the science and engineering practices dimension is a skills dimension. And so what you will notice with the conceptual shifts is that the shifts in concepts are towards those which require skill to develop and use. And that's what Appendix A goes into detail about. Appendix H is dealing with the nature of science and engineering. And so specifically, the nature of science and engineering gives us a definition and really a clear understanding of what STEM is. Okay, so that STEM and its value and its meaning is not really in the eyes of the beholder anymore. It's actually defined in the standards. And the way that the standards approach science is as as a scientist would approach science. Scientists ask questions, and they answer those questions by developing experiments, planning those out, and using their plan to actually carry out an experiment, that experiment yielding data which allows the scientist to reflect back on a hypothetical answer to the question that they're trying to ask and answer. And so I guess just in a very basic sense, scientists ask questions and they try to answer those questions through experimentation, which yields data and provides the basis for claim evidence reasoning kind of model of forming conclusions. So scientists give us scientific knowledge. So that's part of the nature, that's the nature of science. The nature of engineering is using that scientific knowledge as engineers identify and attempt to solve problems, and they use this knowledge to develop prototypes. Sort of they design the first technology of its kind and test it, and they gather data, and they use that data to form an evidence-based conclusion about whether or not the prototype solves the problem. So if it does, that gives us technology. So when engineers successfully solve a problem they've identified with their prototype, that prototype then is technology which is scaled. And so that's the nature of engineering. And this forms a kind of cycle of innovation and so on because the technology enables scientists to ask and answer new and deeper questions. And of course, as they do that, that's building the knowledge, the base of scientific knowledge, which engineers, of course, can use to solve problems they've identified, or even those that have been solved in ways that perhaps could be improved upon. So at a high level, this is at the root of why we have new science standards, because in order to engage in answering questions as scientists do or solving problems as engineers do, it requires skills, and those skills are teachable. The reason you see math in the center of it all is math is a tool for quantifying, so in a sense measuring those observations, really moving from the subjective to the objective world. And that's the thing. We think about scientists doing experiments and engineers developing prototypes and testing them, which is in a sense kind of an experiment. But they each have their own processes. There's a scientific process, an engineering design process, and math in these processes help to make the types of answers that we come to as scientists and the types of solutions we come to as engineers as objective and replicable as possible. And so part of that role of math is to quantify, but it's also to help analyze and communicate. So things like, bluish, greenish, bubbly, fizzy, so on, is all subjective. Blue to one person may be more green to another person, and so on. But if we can actually quantify something, 3 meters is the same to everybody because it's an actual standard unit. It's quantifiable, it's objective. So math has a central role in the nature of science and engineering, which is why we see it applied within these next generation standards. The other thing to think about in terms of why these standards exist is really this demand for higher order thinking. A lot of people think, oh, what you need to do is start with lower order thinking and build up. And that's really the backwards way of doing things. These new standards really require those higher order thinking skills of creating, evaluating, and analyzing to be something that happens simultaneously in our classrooms and in the kind of instructional learning environment that we create, that full inquiry environment. And just because something's hands-on doesn't mean that it's at all creative, evaluative, or analytical. If you do a demonstration and show students how to do something hands-on, and then they all go do it that way for themselves, then all they have done is remember what you did and mirror it back or parrot it back at their desks. They just happen to do it hands-on. Creating that highest order of thinking is really about taking information and extending it to create something new. So when you think about answering a question or solving a problem, it's really about planning in such a way that somebody hasn't told you what the plan is here. It's your own idea. And then you carry that out and you get data that's novel, it's new, it's unique to your idea. And by you, I don't mean you, the one individual student, but it may be a pair of two students in a small sort of group learning environment. And sure, you know, most likely it's hands-on. That's the easiest and I think best way to do this. But you know, how you structure this next generation environment is really key. And these new standards are structured really around students being able to be scientists and engineers and learn by being scientists and engineers in the classroom. And by doing so, creating answers to questions, solutions to problems, and in the process of doing so, using the scientific process and engineering design process, evaluating and analyzing their own ideas and those of their peers simultaneously. Yes, it requires remembering, understanding, and applying, but anytime you create, you are pulling all of the skills below that level of thinking. Same thing with evaluating and analyzing. So as a team, when you're unpacking these standards, what you need to think of once you have gone through these, the front matter, and then in-depth look at the conceptual shifts and the nature of science and engineering in appendixes A and H, is really at the structure and design of the performance expectations themselves. And so this is a key shift in and of itself, is that the next generation science standards word standards is kind of a bit of a lark, because they are in fact performance expectations, and that's how they are referred to in the documentation. So again, going back to that same website link, nextgenscience.org/get-to-know, with the dashes needing to be in there, what you want to do is read sections titled structure, and again you're going to see that down here, structure, when you're on that website. And appendix is E, which is an in-depth unpacking of the disciplinary core ideas, progressions. Appendix F, which looks in depth at the science and engineering practices, and Appendix G, that looks in depth at the cross-cutting concepts. Just a quick note about these three. These three appendices are unpacking the three dimensions of the performance expectations. And just as you see in the title of Appendix E, each of the three dimensions of the performance expectations are progressions. So they're not something, despite they're going, that depending on what grade level you look at, or even what state you're from, because each state, even if you're in adaptive state, you know, the reason why most states who are not adopters but are adapters did this was for political reasons, to kind of break the tie with the title Next Generation Science, sort of learning from the, you know, the kind of situation that unfolded with Common Core, where everybody sort of adopted this Common Core thing, and then, you know, these sort of half-baked implementations created a lot of upset and backlash, and it just blew nationwide, where, you know, the upset may have been in New York, but suddenly, you know, it was spreading other places where people were kind of like, maybe we should be upset with this too. And so anyhow, so that's one kind of element and reason why that happened. Another one is, you know, unfortunately, lobbying. And so when you look in places like Massachusetts and West Virginia, the effects of lobbying are reflected in the standards. I think there's a strong case to be made for that. And there's, particularly in West Virginia, there's a good amount of documentation in the media which you can just, Google West Virginia Next Generation Science, and you'll see that that there's a lot published about that. And it's unfortunate because I think it creates another level of confusion for folks that have to function in an adaptive state, because they have to sort of understand the next generation science standards and unpack them, and then go and apply that knowledge to the adaptations that were made in their own state, and try and figure out the logic. Was it political? Was it, for local industry and workforce development reasons, or was it simply to just break ties with language that might, help isolate that state from backlash, if any of that occurred at a nationwide level? So anyhow, no matter what, adopter or adapter, a little tongue twister there, you should look at these 4 sections, and the fifth being Appendix I, which is engineering design in the NGSS. And a quick note about this: the engineering design appendix talks an awful lot about engineering and applications of science and engineering. And when you read things like, science and engineering is not prescriptive, absolutely, and it's nonlinear. There's a couple statements here and there, more in some earlier documentation, that talks about science and engineering not being linear. And there are some quotes that talk about scientific method and so on as kind of an analog. And I just want to kind of unpack that for 1 second right here. Using a process does not mean that you are saying or communicating that science or engineering is linear. Proper process does have direction to it, right? Any process has direction. Just like when you step forward, you have direction straight ahead. But the thing is that proper process, once you have learned something as a result of data and formed a conclusion, then you actually use that to begin pivoting, just the way that you step forward and pivot in order to walk in circles or triangles or in all the nonlinear shapes that all of us spend most of our time walking or running in our lives, okay? They're the result of single steps forward, but then pivots, okay? And it's sort of the way that we go about that. The use of engineering design process and the need for it is absolute in these, and the same thing with science, the scientific process, which many of us are accustomed to as the scientific method, is necessary, and it's a useful tool, because by teaching children process, what we're actually teaching, and if you look at the science or engineering process, it's really a process that mirrors the thinking and problem-solving process. It's actually, I think, mirrors the learning process that our students go through. How, and you can think about this as a scientist, how do I go from a question to an evidence-based conclusion? What are the logical tools and framework that I should engage in order to get from that question to a conclusion which makes a claim about an idea and backs it with evidence and reasoning? On the flip side, as that kind of that engineering design process, how do I go from a problem I've identified to an actual conclusion about a prototype that I've tested, and the kind of claim and evidence and reasoning that I need to back that up? So when you think about that, those are skills which are easily able to be generalized and useful in any discipline. So I go into this in detail just to say that when you look at Appendix I, it uses a light touch, and I think it's because nationally there hasn't been a lot of thought about engineering, and there have been a few kind of these trite models that have been developed, and some that are kind of overreaching as well, with bubbles with arrows in 10 directions and so on. So they're disorienting, and they haven't been unpacked because they involve stages like plan. Well, there's a lot of things that go into a plan. So your process can't have the stage called plan, because you need to unpack that in the context of K-12 so that children can actually develop useful skills and gain momentum and understanding of the process that they can then move forward with. So in the case of No Atom process we've developed, just to give you an idea, I don't have a slide of it here, but just to give you a sense, we've developed in the context of science, in the context of engineering, an 8-stage process, and we've used this with hundreds of thousands of students and thousands of classrooms, and frankly, it's very age appropriate, and it does have direction to it, but it also pivots, and that's a kind of home for the science and engineering practices dimension of the standards. So when you think about the standards, think of practices as being the skills that students develop, the process as being another kind of framework which combines skills and logic so that students can progress from a question or problem to an evidence-based conclusion. So reading that Appendix I is going to help kind of tune you in and your team to how, when you think about these next generation science standards, which are, again, performance expectations, how you're going to need to equip students to be able to demonstrate their understanding. So in the classroom, think about it this way. The classroom is a context where students build understanding. And they do so by building that understanding in 3 dimensions. They build skills, which are the science and engineering practices. They build content knowledge, which is disciplinary core idea. And they build an understanding of the systems. But they do so best by actually solving problems and trying to answer questions. So by being scientists and engineers on an everyday basis, okay, that's how students learn to develop a model, in this case, to describe the movement of matter among plants, animals, decomposers, and the environment. It entirely flips, and I think that this is a key point as you're unpacking these standards, it entirely flips that I do, we do, you do concept of instruction on its head. Because in order for students to be able to demonstrate their understanding, they need to actually engage in rigorous curriculum and instructional environment and pedagogy which challenges students. And that's the thing, the definition of rigor being where challenge exceeds skill. So if you think about it that way, your pedagogy, instructional pedagogy, and your classroom environment needs to, September through June, be presenting challenge which exceeds the student's level of skill. And that is, skill practice-wise, but also their content knowledge and the connections with which they have to content. And in order to do that, what you need to do is shift that model around so that it's a you do, actually putting it on the students to be asking the questions and identifying the problems and challenging them to use the skills that they have and then extend those skills to actually develop and use the content with the skills to identify the connections and actually solve the problems and answer the questions. Okay, and when you look at one of these performance expectations, you can see that there's not a specific context here, is there? When you think about the movement of matter among plants, animals, decomposers, and the environment, there's infinite contexts. When you look at the disciplinary core ideas dimension that supports that, this is not specific to marine or a deciduous forest or the tundra or anything. It can actually be anywhere. And so the expectations here are really key. And so as you're unpacking these standards, it's important to think about and unpack with your team what these performance expectations represent. And so, and specifically, as a result of that teaching and learning environment that I was just describing, really specifically, what is the evidence of mastery? And so where you can find that is to go to nextgenscience.org, and this time it's /evidence-statements. And what you want to do is download and read all of the standards along with their evidence statements. And I just want to pause here and say, don't make the mistake of thinking that when you download the grade 5 evidence statements and standards that those are the only standards that apply to grade 5. You see, the way to view these standards and evidence statements is really as progressions. And so grade 5 is responsible for reinforcing all of the prior grade level standards and also introducing future grade level standards. And that's how you end up with mastering by the end of the grade level the grade specific standards that are mentioned, but also avoiding or reducing those systemic gaps that can occur when you only focus on a standard, once in a child's K-12 experience. So what you want to do is, and when you look at peak alignment criteria, and I'll show you about that in a second, what you want to do is you want to actually be teaching these standards in groups, not in isolation, and in such a way where you're reinforcing prior grade level standards, and so reinforcing those and introducing standards from future grade levels. And that avoids systemic gaps because students all develop differently at different rates. And so once and done is not a good practice or a best practice, but also there's a lot of transience in districts, student absenteeism and many other things that create a problem when you only view something as a standard that happens in one grade level. So if that's in your thinking, somehow you have to find a way to get over that. Now, when you think about these performance expectations, you've got the standard here and those 3 dimensions. This is what those evidence statements look like. So this is the evidence statement that supports or is behind this one standard. And so when you think about an evidence statement, it is the observable features of mastery, and from a student, as you're observing a student performing, okay? And again, these are intended to be by the end of the grade level. When you see this, you see a lot of sort of unpacking, right? So a student in the context of that standard who will be developing a model to describe the movement of matter among plants, animals, decomposers in the environment, well, they could be given a picture of any ecosystem. And as a result of being given that picture and a prompt, that student should intuitively be able to develop a model to describe the matter movement and the plants and animals and the relationships between the plants and animals and the decomposers within the context of that environment. So you think of food chains and food webs, okay? And the thing is this is not going to be the result of you showing students, here's a food chain, here's a food web, and then having them go and do it for themselves. It doesn't work that way. It's really this other way around. It's a context or a scenario. And so yes, in a picture there are plants, animals, and decomposers as part of that environment, but the student should be able to talk about the relationships between them. Specifically, how is it that the plant is serving as matter, as energy, as food for certain animals, and how some animals provide that for that resource set for other animals, and where does that even come from to start with in the case of plants, and the role of energy transfer from the sun to these organisms, and how there are decomposers that play a role as organisms sort of exit being a living organism through that life cycle, whether they're being consumed or just sort of naturally passing, so that their matter and energy is being returned to the environment to be then reuptaken into the food chains or food webs. And so that's where you get into these sort of phenomena dimensions of cycling of matter, cycling of energy, and how it's not really the issue of a single food chain, but a food web and so on, and how species interact and are adapted and play unique roles in these ecosystems, and how you can actually have affects within ecosystems where an input or an output can create a shock that changes. Having more grasshoppers may result in more frogs, and more frogs an increase in frog population may reduce the population of grasshoppers, but then increase the population of snakes and so on. And so over time, you can actually see environments changing and cause and effect relationships and so on. So you can imagine that a student is not, in a classroom going to today learn about plants and tomorrow learn about matter and the next day learn about animals and so on and so forth. That's an old world pedagogy and instruction that is based on that old type of standards of fact recall and memorization. This is really combining the content with the context. And that's the thing, is content and context are really linked in these new standards. And then requiring the student to have skills or have developed skills which they use to then develop and use that content and context. So basically, when you think about how this one grade 5 life science standard plays out, and a student who's mastered it, a student came to understanding within these 3 dimensions, and a student who's mastered it is going to be observed pulling all of these elements together in a novel context. And so to get there as a team, when you think about unpacking these standards and really learning what the performance expectations expect of a student, you have to really think about that expectation as being something a student has to learn. They learn it in the classroom. It has to be supported in the classroom through pedagogy, through the hands-on materials, through the lesson plans and so on, which teachers are executing. And so the question becomes, well, where does that material come from? And every school and district has their own sort of philosophy on this. There are certainly schools of thought and groupings that are out there. So your school or district may be of the idea and mentality that teachers develop this. And so when a teacher goes home at night, they're going to spend their time looking at the standards and going through this progression, trying to go from the standards to actually developing district curriculum. And that district curriculum, they're going to break that down into the district's teacher background, the lesson plans, the assignments, and as well as the assessments that are part of that, and the actual sort of experiences and boundaries and so on that are grade level specific and that are nurturing at each of these grade levels from September through June and from one grade level to the next, so that that student experience comes to life and is really consistent and is achieving the goals really, and that's where the goals of that student experience is student learning. So what do we mean by student learning? It means that students have been given the opportunity to develop an understanding by having that you do type model, and then if necessary a support for a we do, kind of that thought partner transition, right? Because we want a full release of responsibility under these standards. And so the problem with the I do, you do, the I do, we do, you do model is that if I do and then we do, what is left for you to do? And the reality is that that model strips rigor out of the experience right away, because if I've done it and then we've done it, by the time you've done it, there's no challenge, right? And what we know from brain science is that, in fact, when it's the other way around, and specifically when students are building a framework of understanding and a framework of skills, and that's the difference here. When it's you do, you're building a framework. Students have to start with what they know, the skills that they have, and actually develop and use them and extend them into an area that's unknown, and that's what the next generation science assessments at a state level look like. That's what the emergent and operational standardized tests look like. Just look at DC and Illinois as examples. Quite frankly, these are just like PARCC assessments. There's even Smarter Balance or whatever ELA assessments that you are now using. Most states are now using in an ELA context performance-based assessments that require students to analyze scenarios or passages and then actually provide this claim evidence reasoning model of response to those. And so it requires creating, evaluating, and analyzing creating a response and a hypothesis or a claim and a claim, which is supported by evidence and reasoning. So again, evaluation and analysis. When you think about it that way, that's what the classroom in science is going to be requiring as well. Okay, and these new assessments are going to be requiring, they're going to be scenario based, so you can't just show a student, here's a food chain, grasshoppers eat plants, toads eat grasshoppers, and snakes eat toads, and hawks eat snakes, and that's a food chain. And then if you add this other food chain in, now you have a food web, and that's it. A student actually, and the reason that I think even from a brain science standpoint, we could talk about that, is that the retention is very low in that situation because students haven't built a framework. They are trying to remember and recall and retain through rote learning processes, mapping word to definition, word to definition, word to definition, instead of trying to observe context, consider context, link that, concept to concept, concept to self, concept to world, and then develop and use it with skills that have a purpose. And so coming back to how you unpack that as a team in its connection to standards and curriculum development, you have to be really focused on the standards shaping sort of the boundaries, just like turning the headlights on the highway at night. You can see the yellow line and the white line. And, this is how we approach it at NOADM. Kind of helping create the boundaries at a curriculum level for that student experience, so that every student is not engaged in a rote process, but in fact is able to bring their own ideas to life, build a framework, and that's where we get the student learning. And as a result of having built that framework, students can be challenged in these standardized assessments or just in life, and they can then demonstrate evidence of learning through those observable characteristics of mastery, which we, in this one case, this example we used earlier, which you see unpacked here in these evidence statements. So I'm sorry to take a long time and talk about that, but it's really important when you think about that progression. If you're putting all of that on teachers, it's an awful lot to ask, because frankly, when is a teacher individually going to do all of this? And then if you expect at a district level that every teacher does this individually, then you have 400 or 1,000 teachers in your district that are all going in different directions, which is a kind of problem in and of itself. So if you think of it that way, curriculum really comes higher up. It at least comes at a district level, and so you have to think about what resources you have available to do that. And if you don't have the resources, then thinking about the resources that you're going to put in place to actually go out and find that and ensure that it's actually aligned. So thinking about what people are struggling with now in terms of these next generation science standards, it's really, I think, starts here with this traditional model of science instruction that teachers have all, if you are a veteran teacher, you most likely were taught this in school, in teacher school, if we give it that, kind of name. And so, the idea that content flows through a teacher, and that teacher's job is to model the facts, demonstrate the phenomena, explain what that content is, right? And I just was explaining to you how that's exactly what we don't want to do, right? It's I tell you, and then you tell me what I told you. And if you can tell me what I told you, we'll just keep this up all year long, and I as a teacher will do the telling, and you as a student will do the listening. And if you're proficient, that means that you can recall the facts, repeat the demonstration, or summarize the phenomena. And that's a very, very rote definition of proficiency. And the thing is that when you look at these new standards, they really were birthed from National Academies of Science and Engineering, and the National Research Council really helped get the ball rolling. And this is the definition, the new definition of effective science instruction, or science and engineering, or STEM instruction. Okay, effective science instruction capitalizes on students' early interests and experiences. It identifies and builds on what they know. It provides them with the experiences to engage them in the practices of science and sustain their interest. So it's not what you see on the left, the I do, and then you go back and we'll do it together, and then you do it on your own, so everything gets done 3 times, and this kind of way that strips rigor out of it, to something where students have maybe read about something, had a Socratic dialogue, and then they're using their skills to try and solve a problem or answer a question, on their own or in these small teams, like these 2 students are doing. Planning out an investigation, in this case as engineers, to try and solve that problem and then carry out their own ideas. So the thing is having specific unit progressions and context is really important. What that does is it gives you the opportunity, first of all, to start early, kindergarten, pre-K, and so on, and intentionally build year to year. So you're building on interest and experience that way. But from September through June, by having specific unit order and lesson order such that those ideas are scaffolding and those lesson plans are scaffolding, what you're doing is identifying and building on what children know, right? And providing those students with experiences to engage in the practices means actually engaging students in the challenge of the skills required, not by showing them, but by actually involving them in using the skills to develop a question into a plan, and then into an actual hands-on experiment, and then into, through that data and a conclusion. That's that claim evidence reasoning. That's how you engage students in the practices of science. And you also sustain their interest because they're bringing their ideas to life, and that's really, really key. So the next generation model of instruction looks like this. It looks like students developing skills, which are those science and engineering practices, and directly using those science and engineering practices to develop and use the disciplinary core ideas and the cross-cutting concepts, connecting the 2 together and using them, and developing and using them in order to answer questions and solve problems. That's how students are scientists and engineers under these new standards in this next generation model of full inquiry. The role of the teacher changes because they're not getting between the student and the content and telling everybody everything, right? Their job's not to be a speaker. Their job here is even more skillful. It's to gradually adjust the supports for that student to help them understand how to engage appropriately and to redirect and monitor them, okay? To act as a coach, not as a sage. And now the expectations of a student is different, right? A proficient student in this model is not somebody who has a good memory and who sits in their chair and is quiet and fills in the blank with the word that should be in the blank. Proficiency here is a student who has developed the skills or is using their skills to solve problems and answer questions, and who's actually engaged in developing and using content appropriately, okay, and who's engaged in connecting content to content, content to self, content to world in such a way that they are not only giving evidence of their understanding, but also describing the dynamic interactions across the curriculum. And that's the thing, is these new standards are naturally integrated, okay? So you have to be expecting to be teaching science and ELA in that next generation inquiry environment. So when you think about that, that's why we have these 3 dimensions supporting every one of these standards in the documentation. Okay, the documentation is designed and is laid out so that you can see exactly the practices, the content, and the systems that are most closely tied to what a student's understanding should be as a result of instruction. Okay, and then we can trace that further into those expectations. Now, one of the issues that people face is learning about the content itself, because naturally integrated, and the recommendation is that content is taught across all of the strands. So one of the things that's going to be a challenge for teams, just understanding the intentions of the standards or the construction of the standards, is actually the content itself. Because a lot of folks tried to, in these old fact-based standards, and divide and conquer is really what people try to do. It's like, well, I'll teach these 3 pools of facts a year, and then the teacher in the next grade will teach their 3 pools of facts in their year, and we'll kind of divide and conquer this way. Well, you can't develop curriculum that way with these new standards because we have to think about user experience, right? So you develop whatever curriculum. When you refer to science, if you have 3 people talking about science differently, from a student's perspective, what is science at the end of the day, right? If all of your vocabulary's got 3 definitions to it, you might get any one of 3 from a student. And if the student has encountered those words across 12 grades or 13 grades, then you can expect 39 different interpretations of science. And then if you think of a student learning a couple hundred vocabulary words over the course of a school year, 39 multiplied by a couple of hundred is an awful lot of permutations and confusion from a student standpoint. But on the flip side, from a teacher standpoint, a teacher needs to not only be teaching earth science or life science or physical science, they actually need to be teaching across all 4 strands, earth science, life science, physical science, applications of science and technology, and chemistry. And so as this sort of shift in unpacking is occurring, some folks are going to be dealing with content that they're less comfortable with because they don't, especially if they're shifting out of a traditional model of instruction where it's that old I do, we do, you do model. There's going to be this level of discomfort. So, and I don't care if you are talking about high school teachers, middle school teachers, or elementary school teachers. And frankly, it tends to be easiest for this transition to happen at the elementary level, which might cause people to sit back in the chair and go, what? The reason is that teachers are more often used to learning along with the children, talking about lots of different ideas, and not just focusing on one idea and trying to drill it, all year long, the way that a year-long course in earth science might be at the middle school level. So keep that in mind. Learning the content, so how do you do it? Well, any and all resources. Use Google. I mean, that's really the best resource. And as people are encountering things, well, I've never taught about genetics before. What are alleles? What are prokaryotes, eukaryotes? What's an example of an ecosystem? What do voles eat? What organisms eat voles? Those are things that teachers are going to have to be engaged in as you go through unpacking the content, right? Here, you're talking about ecosystems and organisms and decomposers and so on. There is not one that's here. There is not one actual organism that's mentioned. A vole is an example of an animal. And in fact, it's an animal that has a specific food and has a specific place in a food chain and so on. So in order to even begin thinking about going from standard to curriculum, that's where you have this research process that starts to get involved. And again, thinking about the districts who are putting this on teachers, that's a lot of research to do in your, after dinner. And so one of the other problems that happens is people start downloading and just grabbing things off the internet that people, may have even reviewed highly on these, teacher-to-teacher lesson plan trading platforms. And I don't care if it's paid or free or delivered by a nonprofit or a for-profit or whatever. What we're seeing is tons of resources that are traditional resources that have been repurposed and changed to, call themselves next generation, and people are saying, oh, here's where you use this practice and so on. But all they're doing is kind of, having students go through the motion of an I do the practice and you do the practice, and that old traditional model, and trying to get students to recall it. But what's happening also along the way is that we're seeing a lot of resources. So you don't want to do that. But what you also don't want to do is grab something that somebody had that gets tons of thumbs up that are actually resources that teach misconceptions. And this is one of my favorites to point out. These 3 pictures below. Just go on Google and Google shaving cream rain experiment. or clouds and rain with shaving cream and food coloring or something like that, and look at Google Images, and you're going to see these kind of images. And if you look at a kindergarten, first grade level student, one of the common misconceptions is that rain comes from holes in the clouds. And well, that's a misconception that students have. And look at how these professional development sessions and resources are reinforcing that. Now, these resource providers are calling these experiments, but they're not experiments. Students are not engaged in actually coming up with a question, developing a hypothesis, having a plan that's going to result in an experiment that yields data. What this is it's a model that misrepresents how water vapor condensates around a condensation nuclei, like a piece of dust, and actually begins to form a water droplet in clouds, and then gathers mass through that condensation process, and then makes its way from the sky to Earth's surface, or perhaps it doesn't make it all the way to Earth's surface. And so you can see here how somebody puts shaving cream on top of water, and there's holes in the shaving cream. When you drop the food coloring onto it, the food coloring makes its way through and sort of mimics something dropping, but really reinforces all these misconceptions and perhaps creates those misconceptions to start with. And the sad thing about this is that the people in this blog on the right, in the photo credit here and what you see in the center, I mean, this is an educator who is at a university who is teaching teachers right now, and has been doing so for decades, in the School of Education, that this is what you're supposed to do. And it's really unfortunate, because here you have somebody who has a misconception, who's propagating misconceptions, and who's unfortunately propagating them among people who will then go out and propagate them again. So learning about the content itself and actually at least understanding the basics is key. So whatever resources you use, you really need to be sure that they aren't incorrect to start with, that whoever developed them, and in our case, we go through great pains to make sure that the vocabulary and the definitions are very accurate, that it's authentic, that it is actually relevant in today's world, that it's not dated knowledge that has since been replaced, and so on and so forth, and that it doesn't create the opportunity, it doesn't, one, communicate a misconception, and it doesn't reinforce a misconception or create the opportunity for a misconception to develop by misrepresenting, creating the opportunity to misrepresent what actually occurs in real life through these phenomena. So learning about the content itself is really important, and that's really key as you think about the kinds of resources that are out there. You need to think about, is this a basic awareness ready resource that's just going to get students to the level of being able to raise their hand and say, yeah, engineers solve problems, that so I can raise my hand and understand that that's what they do at this company. They hire engineers to solve problems because those resources come from a company that were downloaded off the internet for that purpose, or from a museum. A lot of museums are like malls where people go to spend the day and get a little bit of awareness, pushing buttons and so on and so forth, and become aware that in a certain year something was invented, and can replace your heart, your natural heart, with this artificial one or something. Knowledge readiness is that kind of textbook thing where you think about, in textbooks we see the book explaining all about what scientists or engineers have discovered or done. The old kind of kits, those full option science kits that folks have, many people still use them, and they're just a bunch of tasks that you do with materials, and so students learn to perform tasks. If you need this information, you perform this task. Mastery readiness is about learning the skills that you can generalize and having the curriculum and resources in place to learn those skills and be able to generalize them and develop and use their content knowledge and actually connect that content knowledge across disciplines and to be able to generalize and synthesize with the skills and with the content in order to be able to solve problems and answer questions. So at NOADM, that's really where we aim. And I would say one of the big challenges right now is there's not a critical mass of mastery-ready resources that are out there. In fact, there are very few. We're one of the few that are out there. I think, I'm biased. I think we're the best. But nonetheless, it takes a lot of effort and focus to, go beyond these lower level pieces, and there's just not a critical mass of it out there yet. So when you think about developing and finding well-aligned resources, what I would do is I would point you not to, the shaving cream thing, but in fact, and even things that are teacher developed on these trading platforms, whether or not they get 5 stars, and you have to, Google. I really Google these shaving cream rain things. It's like unbelievable. People think it's great. It's the best thing ever. Real teachers in real classrooms and real professional developers. Like, yikes! Somebody paid to have this taught to their teachers. What you need to do is go back to the Next Generation Science Standards, and I point you to these 2 resources. You can go directly to, it's a long link, which is why I don't give it to you here. It's like, it doesn't barely fit on the screen, but we can redirect you to it. If you go to noadm.com/PEEC-alignment-resources, okay, and that's the peak alignment guide, and that's not a NOADM thing. That is the primary evaluation of essential criteria for alignment for next generation science standards that comes right from Achieve, and they were involved in developing these standards. They're really, when you go to nextgenerationscience.org, whatever, who runs that? Achieve. Okay, so what this resource does is it really shows you 5 key pivots that are required at that school and district level in order to be a school or district that's aligned to NGSS. Now the thing is that, remember, the curriculum scope and sequence and whatever is not curriculum. That's just some basic mapping, right? But that has to exist at a school or district level before have anything else. So the next resource you want to look at is this equip rubric for science units and lessons. So if you've made these 5 key pivots, now what you need to do is you really need to unpack what it means to be a next generation aligned lesson or unit. And a unit, of course, consists of lessons. So think about it this way. The peak is going to talk about teaching standards in groups, and we're, NOADM is peak aligned, and equip, it's NGSS aligned, but we do it through the lens of this peak alignment and these equip rubrics, so we make sure we're compliant really with the best practices and structure. And again, we've been doing this for 12, 13 years, so we're good, and we've been developing these resources alongside the release of all of these standards and documentation since 2009. So that's how we got here among the first. But what this rubric will help you do, so if you go to noadm.com/evaluate-your-science-curriculum-tool-download, and again, I apologize for the length of the link. The other one's longer. And you don't have to get this from us. These are, not ours. Again, this one comes from Equip. This is the Educators Evaluating the Quality of Instructional Practices for Science rubric. Okay. But the long and short takeaway is that this rubric will help you basically evaluate the lessons and units you already have. And it's important that you think about, again, this next generation inquiry environment that's very dynamic, that it's students as scientists, as students as engineers, and that's how they're learning, by actually originally and authentically asking questions and solving problems with their own ideas, developing experiments, and then carrying them out hands-on, hopefully, and gathering the data and using that data to form evidence-based conclusions. So think about this as almost like a drilling down process, right? So you learn about the intentions of the standards as you are unpacking this on your own or in your teacher teams. Then you go into the construction of the standards. Then you actually think about the content, and then you actually drill down into what that alignment is going to look like for your district, needs to look like for your district, and how that alignment needs to consist of units and lessons, which are next generation aligned, and really 21st century quality is, really a key aspect here too. So in the last few minutes, what I'd like to do is just hit the fact that these next generation science standards are performance expectations and they're not standards. So a key takeaway here is that the standards are not tasks. And when you look at those performance expectations, that performance expectation is not a task, and the evidence statements are not discrete tasks either. Okay, the role of curriculum is to translate standards into a next generation inquiry environment that helps children reach proficiency and, in fact, mastery of skills, content, and phenomena, such that they're able to perform, such that they are able to perform the expectations of the standards in an unfamiliar context that is not the result of direct instruction. That point cannot be understated. That the next generation science standards are not about direct instruction. They're about students actually experiencing and developing a framework of knowledge through using the practices and the content in order to solve problems and answer questions. So when you think about curriculum, curriculum actually is built on, and if you're thinking about your development process for NGSS or redevelopment process, it's built on many other things. First of all, it's built on integration across the strands, all of the earth science, life science, physical science, so on, right? That integration, but it's also integrating ELA and math and really focusing on those creative, evaluative, and analytical higher order thinking skills that need to happen simultaneously. So in the ELA context, that's those common core technical subject standards, the nonfiction reading and writing standards, and so on. And that's going to be part of your science time on learning now, right? It's not just the experimenting and prototyping. In a math context, these are all the common core math practices, right? Data collection, quantifying observations, but then actually analyzing them, displaying them visually in graph form, and so on. That's, again, part of developing those creative, evaluative, and analytical thinking skills. That's why these NGSS inquiry classroom environments require a focus at the top level, not at the bottom level, because you can always dial it back. But when you create, you evaluate, you analyze, you're developing skills that are useful in any discipline, whether or not a child becomes a scientist. But you're also achieving the goals of remembering, understanding, and applying anyway, right? So that's why we were talking about thinking about this NGSS model of instruction that shifts the expectations of the student and the role of the teacher into something that's much higher order. So as you start that redevelopment process, you need to start with a team of folks who have a deep understanding of human organizational behavior, because again, the user experience, the user being the teacher, but also the user being in the student, right? We don't want 6,500 different takes on what science and engineering is, and confusing the tar out of students because everybody misinterpreted the district's curriculum, and there were 20 different definitions of science, and everybody that a child encountered along the way referred to a rock or a mineral by a different meaning, and so a student had no idea what the expectation of them was. You have to take that organizational behavior into account, and the team of folks, if you're going to do this in-house, really need exceptional written and oral communication skills and logistics skills to understand the needs of the classroom and develop the structure such that it's really robust. Okay, so we don't end up with gaps all over the place. And so you have to envision the student and teacher experience at the very basis of this curriculum process. The next thing you have to do is be committed to unpacking, as we've talked about today, what are the nuanced progressions and meaning of these disciplinary core ideas? What is the content itself? How does it connect? Okay, and in such a way that we don't embody misunderstandings and create the opportunity for these misconceptions to propagate. Next is taking that content and actually relating it through cross-cutting concepts and having that process framework in place. Like I said, we use an 8-step process for science and an 8-step process for engineering, but science and engineering are different. They have different processes. And so that's really important. First, that you recognize it, and then also that you have a age-appropriate, clear, executable, concrete process that is grade level appropriate and actually can scale with the students from grade level to grade level. Okay, so that skill set gets reinforced and reused constantly. Becomes a habit that and so on. And that's where we're talking about these science engineering practices, cross-cutting concepts, and disciplinary core ideas, all coming together in the context of that process, or processes. Then, before you're not even to units yet, next thing you got to do here is really think about networking those performance expectations. So thinking about how these three dimensions, but particularly the performance expectations, can be grouped in such a way that they reinforce themselves, and they can be put in a progression vertically and horizontally so that students can reach mastery by the end of the year. And also in that process, that it's so grade level specific, but then it's reinforcing prior grade level standards, and also introducing future grade level standards. So that way there, it's almost like hand in hand throughout the year, we are scaffolding for students and really developing this framework, but from one year to the next, each group of educators at each grade level are supporting each other so that it's not this blitz and big question mark when it becomes that 4th or 5th grade test year that we'll find out how the kids do, or that we're going to shut down and do test prep for weeks so that the 5th grade teacher's done their job to get kids ready for their science test with a 4th grade teacher. Every day is preparation and development of skills and content knowledge and an understanding of systems. You don't do that in 3 weeks before a test. And it's every day of the child's academic career, really. So that articulation is what gives way to units. Okay, and so in the context of Adam, this is what something like that looks like. This is our grade 1 to 5 progression. You can see that there's a specific unit for each grade level with a specific order and a specific purpose, and it goes across all of the strands, right? And it builds. And then it goes and builds from one grade level to the next. So students are mastering the grade level specific standards, and that they are being taught in groups, and they're being reinforced when they go to 2nd grade, but those next level of content standards are being developed and reinforced there. Now, what I'll say about this, just kind of quickly, if you look at this one from 5th grade, you can see how we're able to paint a big picture of science, Earth's surface, and we could talk about matter and changing matter there to talk about what makes Earth unique and a unique place for life and how life can exist here and what examples of life look like, things like plants, and how there are these food chains and food webs and how plants actually fit into the larger picture of ecosystems and food chains and food webs and life cycles, and how energy transforms and moves, and how that is even represented in physics, in the physical world, the non-living world, in things like actions and reactions and circuits and electricity and engineering, as we take that content knowledge from science, the scientific knowledge, and actually apply it to solve problems like the need to balance boats and technology for carrying cargo and even keeping homes warm and light and so on as we engineer homes. So just to give you a sense of we can actually help students build a framework all year long when we do our jobs well. Okay, and it's not just 1st grade through 5th grade, but also leveling that up into 6 through 8. Okay, so it's really at this level that, and you see that here, discovering matter, and you see the same themes, but they're at different levels. So students are not getting drilled to death over and over the same vocab words. What's happening is they use the same vocab words, but you are increasing depth and adding to that over time, and there are new angles and new contexts and new opportunities to deepen and practice our skills and answer new questions and solve new problems. And that's where lessons and that content and experience gets formed, and the hands-on materials are decided upon to fit into these units. And that is what forms curriculum. Okay, curriculum is all of these things. It's not just something you download and a demonstration you do in a couple of pages or 3 or 4 pages that you hand to a teacher and say, this is what the district wants you to do this trimester, and these 10 vocabulary words, and you find a way to do that. Okay, there needs to be much more thought and structure and organization that goes into it, so that that teacher can be supported appropriately with the content background, the lesson plans, the content, the experiences, and the unit, order and articulation that's going to bring your team together, eliminate those systemic gaps, provide a great user experience for your teachers, but also for the students. It provides, clarity, but also performance. And so, in the context of NOADM, this is one of those types of progressions that we have developed, sort of that nonfiction reading leading into Socratic dialogue, asking those higher order questions that then lead students to be able to ask questions, identify problems, and begin planning investigations, carrying out their plans, their ideas, hands-on, to develop data, and then be able to form those evidence-based conclusions. And doing this in teams, in small group learning environments where they can then share and debrief. Okay, and in our case, we've built in these continuous feedback loops where we're constantly gathering information through support tickets, and hundreds of thousands of students are using this curriculum and have used it, and that's how we're able to continually iterate and refine. And if a district's doing this on their own, they should be doing that on their own, so that it's not like we create something and 5 years later it becomes effective. It's like got to become effective pronto. Because this is when students have an opportunity to learn it. 5 years from now, that's a different set of students. So think about curriculum, professional development, and materials all fitting hand in glove to support that STEM learning environment. If you want to see what a aligned curriculum looks like, you can go to noadm.com/curriculum and download an example unit and student reading piece that kind of fits together. Obviously, you can't download materials, right? They're physical, but you can at least see how that comes together. And when you see these next generation learning environments, this is what it looks like. Students planning their investigations in small teams, carrying them out so they can gather data. The student team, this is the crane that they envisioned would solve the problem of lifting these marbles, the necessary height and distance. So they are actually testing and gathering data on that. And it can take place on tables, in classrooms, in cafeterias, on the floor, in UN High Council and refugee tents. These are some students that are using our curriculum in Arabic. There's only one light bulb in this classroom. It's a tent. Look, there's no desks. There's a carpet on the floor and some little pads. Okay, no fancy projectors. They have posters. So you get the same behavior, though, this active student learning, student ideas coming together. Okay, and once students have gathered that data, they form those evidence-based conclusions, and then they debrief by presenting their ideas and thinking them, actually workshopping them as they transition from one lesson to the next. Now, these practices do yield impressive results in a spectrum of environments too. So I want to say, just from a data standpoint, this kind of thing's something we've been doing for a while. So I'll show you this environment where in Massachusetts, the average proficiency level is 50%. And this is a school that was below it. And over the course of 2.5 years, they nearly doubled it. They went from 36% to 68%, right? So they have a positive trend, but they actually reached a high of 87%. And the reason you get these little dips is because change in teacher, in administration, and there's also natural fluctuations in student populations. But this was an inner city urban school, 72% low income school, 35% ELLs, first language is not English, and 75% high needs. Suburban districts, you see similar sort of things, 50% to upwards of 80% and sustained, okay, and so on. I'll show you this one here, highest school district in Massachusetts. They even get a bump, and you see, virtually no students in the lower categories of warning, failing, needs improvement, and yet basically 90 so are at these top tiers, almost doubling the state average. And then here's a middle school example. And this is not our testing. This is the state's testing, not ours. Here at now, going from 4% proficient to 28% in 2 years. And this is actually the average in Massachusetts for urban middle schools, and you can see that shift. Look at the warning failing category. Many states would call this below basic, cut in half. And this is a tough school. 64% where the students' first language is in English, 95% are low income, 87% free lunch, and 97% high needs. So with that said, the school is meeting their threshold set by the state, which is these red boxes, and approaching within striking distance and still getting accountability points in all these different subgroups. And that's the thing, is it's across all subgroups that these students are getting benefit from this model of next generation inquiry that places students in the role of scientist, role of engineer, really reshaping that environment so that teachers are supported and they're supporting each other, that they're actually able to function in teams, and instead of focusing on what are the Q-tips that I'm going to need, and I downloaded this thing, maybe you should try this, the kids kind of liked it, to here's what we're executing as a team. How is it that you're actually executing this? How are you actually creating that environment, reaching students where the students are at? How are you scaffolding the language in such a way that students have the support that they need, but we're not stripping the intention of the standards and the skills and the rigor out of it? We're actually protecting the narrative and helping children access it versus, and that's what it's about. As teachers, we're trying to help meet student needs and differentiate. I don't think as a teacher myself that we should be charged with finding Q-tips, spending our own money and our own free time that we could be spending with our children at Walmart. But nonetheless, to each their own. So as I mentioned earlier, you can go to noadam.com/curriculum. You can check out some example of well-aligned resources there. We have them for NGSS adoption states as well as some adaptive states like Massachusetts, West Virginia, and others. Our NGSS aligned curriculum is aligned to California and Missouri. So if you are from one of those who are really adoption states who are like on the edge of adaptation, what you'll be taking a look at there is going to be helpful for you. And a couple other ways, if you found this helpful, feel free to reach out if you have a question. Again, fvidgen@noadam.com. Be happy to respond to you personally. If you have something that's related to curriculum or you're looking for a particular resource, feel free to reach out, or you can reach out to Mary Ellen by telephone, 617-475-3475, extension 2006. She's really great with that. Her email is mdelacy@noadam.com. And you can stay in touch. We post all kinds of free blog post articles about really trying to unpack and reach the needs of learners in this next generation inquiry environment on our blog. So it's noadam.com/blog. And you can find out about these kind of webinars when they come up as well. If you don't get an email, or tell a friend, follow us on facebook.com/noadam or on Twitter @noadam.com is our handle. With that said, if you are in a curriculum adoption cycle, if you are saying, hey, we don't want to reinvent the wheel, we want to try and start with something that's on the mark or close to it, you can take a look at those samples. And if you are looking to purchase something, NoAdam keeps its lights on by actually selling curriculum that's really well aligned and hands-on, inquiry-based, that involves all the necessary parts. Feel free to reach out. We'd love to be able to help you. We have the curriculum, the hands-on materials that you need, as well as the professional development all ready to go, whether it's for this year or next year. And you can reach out to any of us here. You can also go to contact, so noadam.com, and click to contact us there, and somebody will get in touch with you and get you to the right person if that's something that you are interested in or need. If you listened to this webinar and you need a participation certificate, please reach out and we'll get you that to the right person. Thank you again, and I hope to connect with you in the future at some point. I really wish you the best of luck, and I do personally think these standards are great for teaching and learning and for kids, and I wish you luck in the process of that transition. I hope that it's an easy one for you, and that it's something that you'll be able to embrace and grow with, because they are an awful lot of fun to teach and watch students learn. Thank you again. My name is Francis Fidgen. Have a great day.